One of the most profound and indispensable numbers in mathematics is E, approximately 2.718. This irrational constant is the hidden engine behind growth, decay, and countless natural processes, so deeply woven into reality that modern civilization would collapse without it. Every time your phone connects to Wi-Fi, E is there, optimizing signal transmission. Every financial transaction, from compound interest to stock market algorithms, relies on E. The cooling of your coffee, the spread of a virus, the charging of a capacitor, and even the radioactive decay dating ancient fossils all follow E's exponential law. Rockets use E to calculate fuel efficiency in changing gravity. Machine learning models train faster because of E in their activation functions. The very fabric of quantum mechanics and thermodynamics leans on E to describe probabilities and energy distributions. From the spiral of a nautilus shell to the pulse of an electrical circuit, E is the silent architect of continuity and change. It is not just a number, it is the mathematical signature of nature itself. From a purely mathematical standpoint, the number E appears in equations in a pretty deterministic fashion. There are many sophisticated ways in mathematics that lead to the number E. However, one of them is important from a historical perspective, as it is one of the earliest attempts that led to the number itself, the compound interest problem, introduced by Jacob Bernoulli in 1685 in its historical form. He estimated the answer to be somewhere between 2.5 and 3. Unlike Jacob Bernoulli, to understand the problem, we will use the terminology of banks, deposits, and interest rates, while of course keeping the essence of the problem unchanged. Imagine there's a bank that offers a 100% interest rate for a full year. You deposit $1 into that bank. At the end of the year, you'll receive $1 in interest and your $1 capital for a total of $2. There's nothing special about that. Here comes the interesting part. What happens if the bank offers a 50% interest rate per 6-month period instead of 100% for the full year? Even though the nominal annual rate remains 100%, the amount of money you will have at the end of the year will not be the same. Here's how it works. With a 50% interest rate every 6 months, you deposit $1 at the beginning of the year. After the first 6 months, you'll have $1.50. Note that at that moment, your capital has increased by 50%. If you then reinvest this new capital of $1.50 with the bank, at the end of the year, you'll earn 75 cents in interest. Together with your capital of $1.50, your new total becomes $2.25. As we see, even though the nominal rate remains 100%, you're better off by increasing the number of compounding periods within a year. To make the picture clearer, let us see what happens when interest is compounded quarterly. As we would expect, after the compound interest operations, the new capital at the end of the year becomes approximately $2.44. Compared to the simple annual interest, a 44% increase in earnings is obtained. Following the same logic, compounding interest every month leads to a net capital of approximately $2.61 at the end of the year.
Based on our experience, given that the total nominal annual interest rate remains 100%, the following reasoning seems plausible. Since an increase in the number of installments leads to an increase in the total amount of money we will have at the end of the year, is it then possible to become Richfinity, a state of a person who has unlimited money? The answer is unfortunately no, due to the limiting behavior of compound interest, which is upper bounded by the number E. In other words, under the given conditions, it is impossible to obtain a capital at the end of the year that is greater than E.
Now, here's something interesting. One might wonder what happens if we keep the total interest rate not at 100% but at something greater, say 200%. Would that be the key to becoming Richfinity? The answer is still a big no. Furthermore, the exact amount that you could obtain is still determined by the number e, and consequently related to the natural logarithm. Let us see this with an example. This time, assume that our new bank manager is an unorthodox person and does something interesting. In order to attract deposits through high interest rates, he or she assigns the new annual interest rate to be 200%, of course with a very strong business and investment plan. In other words, any customer who deposits $1 will get $2 in interest at the end of the year, so the customer will have a net capital of $3 at the end of the year. Of course, the board of trustees of the bank raises a flag and asks the manager about this seemingly obvious bankruptcy risk strategy. But our manager claims that even though customers are promised interest rates that double their original deposits, the bank will not go bankrupt, provided the money collected is managed appropriately with a very strong business and investment plan. However, the board still objects, not because they dislike the business and investment plan, but because with that rate, there might be customers who would like to take advantage of daily or even hourly compounding throughout the year. According to the compound interest rule, it would be a disaster, since every hour the bank would have to double the amount. But our bank manager states that, let alone hourly installments, customers could claim minute-based or even second-based compounding, and still the amount of money that will be paid back to customers will not exceed a certain predetermined amount. It seems quite counterintuitive.
Just to summarize our findings, we can go back to Jacob Bernoulli's computation and represent it in our contemporary understanding. As you can see from the equation, the total amount of money that we can collect is always less than number e to the power of annual or nominal interest rate, no matter how many installments we deploy. So, we can observe that number e somehow inherently manifests itself when an entity or a quantity experiences growth upon growth, where every bit of progress immediately starts fueling the next.
Up until this point, we have investigated how the number e appears in a precise deterministic fashion. However, the number e transcends determinism and manifests itself in probabilistic scenarios as well. Due to the presence of uncertainty, we will now benefit from the concepts of probability at a mild level and show that the number e appears inherently in nature. But first, some preliminaries. Assume that we roll a fair die and record each number that turns up. Furthermore, when a number turns up, we register how many times that result occurred in a separate place. Since we assume that our die is a fair one, it is natural that the probability for each number facing up is equal to the others, and its value is 1/6, or approximately 16%. In a real-world experiment, this value might not be exactly 1/6 due to imperfections in the experiment or a finite number of trials. However, in an idealized version, we can safely assume it to be 1/6. Now, if we repeatedly roll the die and record the outcomes, the probability value of 1/6 starts to emerge in the recordings automatically, when we divide the number of occurrences of any individual possible outcome by the total number of rolls or trials. As can be seen, the value 1/6 is equal for each and every individual face that turns up. Such a behavior in probability is named a uniform distribution, where each possible outcome from a probabilistic perspective is indistinguishable from another. From a pure mathematical standpoint, it is clear that the probability assigned to any distinct event is 1 over the total number of unique, distinct, legitimate outcomes. Since our fair die has 6 unique, distinct, legitimate outcomes, the uniform distribution automatically assigns 1/6 to each outcome without distinguishing them from each other. Here's an interesting question. What is the expected number of die rolls required for the cumulative sum of the rolls to exceed the maximum face value of a standard 6-sided die? To imagine this experiment, say we roll our die the first time and the result is 3. Since we have 3, which is not greater than 6, we roll one more time. On the second roll, assume the result turns out to be 5. So our current total at this point is 3 plus 5, or 8, which exceeds 6. Therefore, we say experiment 1 is a 2-roll experiment. In experiment 2, we roll our die the first time and assume that it turns up 4. So we roll one more time. Assume that the second roll turns up 2. Our current total at this point becomes 4 plus 2, or 6. Since we have not obtained a sum that is greater than 6, we roll a third time. Without looking at the third result, since any value causes the sum to exceed 6, we can comfortably say that experiment 2 is a 3-roll case. By the same argument, experiment 3 requires 2 rolls, experiment 4 also requires 2 rolls, and experiment 5 is a 3-roll experiment.
Now we are ready to go back to our question. What is the expected number of die rolls required for the cumulative sum of the rolls to exceed the maximum face value of a standard 6-sided die? With our current understanding and the help of the notions of experiments and average roll lengths, we can rephrase the question this way. What is the average roll length of an experiment? In the demonstration scenario, we have 12 rolls in total across 5 experiments, so the average roll length is 12/5, which is equal to 2.4. At this point, we can have 2 extensions to the original question. What happens if we carry out infinitely many experiments with our standard 6-face die? And secondly, what happens if we increase the number of faces of our die arbitrarily? For example, what would be the case for a dodecahedron die, for an icosahedron die, or for a hypothetical 100-faced die? Here is the answer. As can be seen from the graphic, the average roll length increases very rapidly at the beginning, namely for the first few die types. But right after that, even though it keeps increasing, the rate of increase gets smaller and smaller. And as we increase the number of faces to be arbitrarily large, the roll length is upper bounded by the number e. In this episode, our journey reveals the profound truth. The number e is far more than a mathematical curiosity. It is the universal signature of continuous growth, the fundamental cap on compounding, and the hidden probability in seemingly random events. From Bernoulli's bank to a rolling die, we've seen how E emerges as a natural limit and unwavering constant in a universe of change. But its power extends far beyond these classic domains. In the cutting-edge world of artificial intelligence, E is the silent powerhouse driving the revolution. Every large language model, like ChatGPT, relies on neural networks. At the heart of these networks are activation functions, the decision-making nodes that determine what a neuron passes on. The most critical of these is the exponential function, e to the x. This function, defined by e, allows models to learn complex, nonlinear patterns in data gracefully and efficiently. It provides the smooth, differentiable curves essential for backpropagation, the algorithm that allows models to learn from their errors and improve. Without E, the sophisticated reasoning and generative abilities of modern AI would simply not be possible. It is the key that allows machines to model the nuances of human language and thought. In essence,
E bridges the gap between the abstract world of mathematics and the fabric of reality itself. It governs the growth of money and populations, the laws of physics, and now the very architecture of intelligence. It is the irrational constant that makes our rational world possible, the most important number you've ever barely noticed. Thank you for joining us on this incredible journey through the mathematics of our universe. If you enjoyed unraveling the mystery of the number E, please hit that like button and subscribe for more deep dives into the hidden math that shapes our world. Stay tuned as we continue to explore the cosmos of knowledge, one frame at a time. Until next time, keep questioning.